right, so let's talk about the second part of this descriptive statistics, which is to talk about variability. Okay, so variability goes right along with the sort of mean, median, mode talk, because again, when we have distributions, the things we tend to want to know about them is what is their shape, what's the most common, way of, what's the most typical, common sort of response, right? And then how much do people vary away, or how much do scores vary away from that most common, most frequent value? Okay, so central tendency we talked about before can be thought of as the mode, the most frequent, the median, which is really the center, which is where it becomes this idea of central tendency. Really sounds more like the median. And then you got the mean, which is the mathematical or arithmetic mean, where it adds up all the scores, divides by the number of scores to get you a true average. So variability goes sort of hand in hand with that. Once I know what the most common person or common score looks like, or what the central tendency looks like, and now I want to know, well, how closely do the rest of the scores sort of follow that central tendency? Are the scores fairly homogeneous? Are they varying quite a bit? So that's what we're talking about now. So this is not meant to sort of fat shame Jonah Hill or anything. I'm not a skinny dude myself, so I know how it goes to sort of fluctuate back and forth. It's just the idea of sort of trying to get you an association in your mind. You've seen sort of Jonah Hill in very thin, and as a sort of bigger actor, he's a very funny guy, and he became famous, in a way that seems to go against the Hollywood norm. It wasn't like this. He started off as this sort of overweight, sort of awkward kid, and that's what actually got him into a lot of movies. And then as he sort of lost weight, he became sort of a better looking, better built guy. You actually don't see him in as many movies anymore. It's sort of an odd story. The point here is I'm trying to make an association between when you see Jonah Hill this way, Jonah Hill this way, it's in a sense that's the same Jonah Hill, right? The internal part of Jonah Hill is the same personality, same everything else. All that's different is here you're getting a sort of wider version of Jonah Hill, and here you're getting a more narrow version of Jonah Hill, which is this idea of what's the difference between these two distributions. If both distributions have a mean of 10, they're both reflecting the same average information. The difference really comes down to, well, how wide, how much variability is there around that central tendency, where here there's a lot of variability, right? This score of 10 is the mean, but scores vary quite a lot away from that number. So you're getting the sort of wider version of the same information, where here you're getting a narrow version of the same information, where this, even though they have the same mean, these two distributions are telling you different things. This one's saying, all right, 10 is the mean, but it doesn't really reflect all the scores in this distribution very well because they differ quite a lot. There's a lot of variability. Or here, right, this 10 is a better reflection of the scores in this distribution than it is in that distribution, because scores here are more similar to one another. They're less variable. They tend to take on a score similar to 10 more often than they do in this distribution. Okay, so again, I'm just trying to get you to associate, maybe Jonah Hill, just make a mental association between that and sort of variability, that there is a lot of variability in his size, but in size are reflecting the same information. Okay. Oh, no. So the way we think about variability can differ quite a lot. Okay, so there's very simple ways of thinking about variability to much more complicated ways. So the first part is the range, which is the simplest form. We just take this largest value in the distribution and the smallest value, you subtract them. And it's sort of like the mode. It's not really like the mode. It's sort of like the mode in the sense of it's simple. It's just a very crude, simple way of thinking. If I have multiple distributions, I can subtract the maximum and minimum values from each one of them and see which one actually spreads out the most, or has the largest range. That's one way of thinking about variability, and it actually makes perfect sense, and it's nice and simple. The problem there, though, is the maximum minimum scores may be outliers. They may be exaggerated because of outliers or skewness or something, and that can actually make the range seem a lot larger than it really is. Okay, so there's something called the interquartile range that helps to sort of cut off the 25% of the largest scores and the 25% of the lowest scores, and it looks at the range of the middle. So it gets rid of the outliers and tries to look at the range for the scores in the center of the distribution instead. So these are, again, looking at ranges, looking at just the ends of the distribution. But instead, it's often, we often will look at, instead of thinking about what is the range in that way, let's look at, all right, well, go back to this picture again. If this is the mean, we could figure out, well, okay, well, how much are people deviating from the mean on either side? On average, how far are scores deviating, either higher than or lower than the mean on both sides of the distribution? And we could figure out then what, on average, how much scores are varying away from the mean. So instead of thinking about the ends, we're thinking about how much are they varying from the center, from the central tendency. So that's what the variance and standard deviations are looking at. Let's take each score, subtract the mean to get a deviation, and we're going to square those. And the reason why we're going to square them is because if we don't, this top part will always be 0 or very close to 0. So we're going to take the squared difference between each score and the mean, and we're going to divide it by this weird n-1 thing. Instead of dividing it by n to get an average, you're going to divide by n-1, and I'll explain that more as we go along. But this version is what we think of as the sample version, or the population estimate version, where we take the deviations, we square them, and divide by n-1. We tend to call this the sum of squared deviations, or sometimes just the sum of squares. And this is the degrees of freedom on the bottom, sum of squares over degrees of freedom. So sum of square differences, or sum of square deviations over degrees of freedom, and we'll talk more about that shortly. But this is the variance. The problem with the variance is it's in squared units, which is sort of weird. So we figure out what the variance is, then take the square root of it to bring it back to the units that it was measured in originally. And that's our standard deviation. And again, it's the same sum of square deviations over degrees of freedom. And it's all relative to the mean, because we're using the mean to figure out how much scores are actually varying from that central point. Notice it's not the median here, it's not the mode. We're using the mean specifically. Okay, again, because it has that this idea of being unbiased estimate of the population, we tend to like the mean a lot more than the median and or mode. Okay, so the variance is in squared units, standard deviations in regular units, because we take the square root. So if you ever ask a question where you're given the variance and asked what the standard deviation is, you don't need to do any work. You just need to square root the variance to get the standard deviation. If you're given the standard deviation and asked what's the variance, just square the standard deviation, and there's your variance. They're the same thing. They're just in two different metrics, two different versions. One is in squared units, the variance, and the other one is in the units that the variable is originally measured in, where we take the square root of the variance. All right, let's talk a little bit more about some of those. To talk about the interquartile range, so the range is easy. I don't need to go in any more of that. Take the largest, take the smallest, divide, subtract. That's it. To do the interquartile range, we need to take a detour for a second. So this part, that if this detour, you need to like focus, because this could be a little weird for people the first time they start thinking about this. But let's talk about what is a percentile and a percentile rank. Percentiles can sometimes throw people off. most of us understand percentages, right? That, you know, if you're doing something and you're in the, you know, it's 80% or something, that means you like on a math test or a stats test, you get 80%. It means you answered like 80% of the questions, right? You got 80% of the questions correct, which is like a B or something in a typical cutoff criteria for that. Percentiles are a little different. Percentiles are having to do with where do you place in the distribution of scores. So not based on some concrete criteria, like you had 100 questions, you answered 80 of them correct. Percentiles or percentile rings have to do with where your score falls within the distribution of scores or scorers in the class, if you want to use the test example. So percentiles will take a distribution and will cut it up into 100 pieces by making 99 cuts, right? P1, P2, P3, all the way through P99 makes 99 cuts to give you 100 different pieces throughout the data set. And that's, we think of that as percentages. Percentiles are the same, just how we're going to use it is a little different. So if that's true, we can cut the data up into 4 chunks by making 3 cuts. We can cut it at at Q1, at Q2, and Q3. So quartiles, you know, they're referred to as quartiles, and people get a little bit confused. But it's not that confusing in the sense of Q1 is the same thing as P25. So if I take the 25th percentile, that's the same thing as Q1 or quartile 1. Q2 is the same thing then as P50. And so, which is the same thing, by the way, as the median. It's the value at the 50th percentile. Q3 then becomes this, or not becomes, is the same thing as P75. Right, so these correspond to Q1 is the 25th percentile, Q2 is the 50th, Q3 is the 75th. Those all correspond. So you're probably thinking, well, if it's called quartiles and we want 4 things, why is there only 3 Qs? Because think about bread for a second. If you had a loaf of bread, okay, here's my loaf of, you know, I don't know, cracked, you know, wheat or something healthy, I don't know. If I had a loaf of bread and I wanted 4 pieces of bread, 4 slices of bread, how many times would I need to cut it? So if you're thinking, well, if I want 4 slices, I need to cut it 4 times, here's what happens. Here's why that becomes a little tricky. If I cut it 4 times, 1, 2, 3, 4. How many slices do I have? I have 1, 2, 3, 4, 5. Ah, crap, I screwed something up. So if I take my loaf of bread and I cut it 4 times, I'm going to end up with 5 slices. So if I want 4 slices, I can't cut it 4 times. I got to cut it 3 times. All right, let's go back to my loaf of bread again. All right, maybe like some sourdough or something. I don't need lunch, I'm just hungry. So there's my loaf of bread. Okay, it's got a little, let's do a little, make it a little. Okay, if I want 4 slices of bread, and I cut it 1, 2, 3 times, I now have 1, 2, 3, 4 slices of bread. Which is why when I want quartiles, I want to cut my data into 4 pieces. I'm going to make 1, 2, 3 cuts, because from 0 to 25% is 1 piece. There's 1. From Q1 to Q2, right, going from 25 to 50 is piece 2. Going from 50 to 75 is piece 3. Right, this piece here. And then going above this, 75 up to 100%, is my fourth piece of the data. So to have 4 pieces, to cut my data into 4 chunks like that, I need to make 3 cuts that actually make them into 4 quarters, 4 quartiles, okay? Then you have another, you probably will see these a lot less, deciles. Deciles are just another form where percentiles are 100, quartiles are 4, deciles are 10. So like deca, has to do with 10. So I want to make 9 cuts to make 10 different chunks of data. That means that D1 corresponds to P10. D2 is P20. Right, you get the idea. This is they're just corresponding to the percentiles, just using 10s instead of 100s. Right? So on and so forth, all the way to this is P90. Right? So all the way through. Right? So they're just, this is just the cutoffs for percentiles at every 10. I call them deciles, which sounds cooler, I guess, than percentile. But they're deciles, they're tenths of data. Okay, so far so good. Percentiles cut things up into 100s, quartiles cut things up into 4s, deciles cut them up into 10s. Okay, so let's talk a bit more about some of this stuff. There's different ways of thinking about percentiles or percentile ranking. So a percentile rank and a percentile are slightly different. Let's talk about those. Percentile ranks are typically a little easier. So what percentage of scores fall below a particular score that exists in your data set? It's actually relatively important that it exists. So it's a score that is actually in the data set you have, right? It exists in your data set. And I want to know, okay, well, what percentage of scores fall below that score? So for that, you're going to use percentile rank, right? So there's you in distribution, right? And you want to know, well, how many people scored lower than you? Maybe this is like height. This means here you're at the 80th percentile. You have a percentile rank of 80 because there are 80 people, or 80% of the people below you in that distribution. To find the percentile rank, we're first going to find the rank of each of the data points, which sounds fancy, but it's just really, we're going to find the position, the order with which they are in the data set, with a couple of tweaks here and there. We're going to subtract 0.5, and it's always 0.5. It's just 0.5 is a given number, it doesn't change. There's a reason for that, because if you actually look up percentile rank in, say, on Google or something like that, you may actually find it with different versions. Sometimes you'll see it with a plus 0.5. Sometimes you'll see it with no 0.5. Okay, there'll be no 0.5 at all. However, the most common way, meaning the way that you will find most often, like in places like Excel, SPSS, SAS, R, those kind of things, is to subtract 0.5 from the rank, divide it by n, the number of scores you have, and then multiply that by 100 to make it into a percentile. If you don't multiply by 100, then it's just a proportion, which is fine, but multiply by 100 to make it into a percentile. Okay, so you're going to use this when you have a score, specific score, and what you need is the percentage below that score, and that's where you're going to use the percentile rank. Okay, so what the hell is a rank? Right, we're talking about the rank of the data. Well, what does that mean? Let's talk about the rank. So if you have a data set in which there are no ties, meaning that there are no repeat numbers, none of the numbers repeat at all, then the rank and the order number, position number, are the same thing. So the first thing you need to do is put the numbers in order. So they're in order from smallest to largest. Then all you need to do, if there's no ties, no repeats, is just say, okay, this is the number in the first position. This one's number 2. This one's number 3. Number 4. Number 5. 6. 7. And 8. Those are the ranks. So 6 has a rank of 5, 5 has a rank of 4, 3 has a rank of 2, so on and so forth. Okay, so the ranks and the position numbers are the same. There's no difference. So what happens if you have ties? Like you have some repeats down here. There's a 6 and a 6 and an 8 and an 8 and an 8. What I recommend that you do, so what we're going to do is we're going to assign midpoints to any ties. But to keep from screwing this up, I would definitely write out the position numbers first and then move on to fixing the ties. And here's why. I'm going to do it without writing the order numbers first, and you see if you can figure out where I screw this up. All right, so this one's the first one. That's easy. That one's number 2. Awesome. There's no ties yet. Here's number 3. Okay. So here I have 6 and 6. So that normally would be 4 and 5. All right, are my 2 position numbers. But because it's a repeat number, I'm going to go 1, 2, 3, 4, 5. So that means this is 4.5 and 4.5. All right, cool. Then I'm going to go 5, 6, and 7, which is what happens often if you don't watch what you're doing. Because I see 4.5, 4.5. Oh, the next rank is 5, and then 6 and 7. What happened there is that I skipped a rank because I didn't sort of pay attention. So if I write down the orders first, 1, 2, 3, 4, 5, 6, I have to move it up a little bit, 7, and 8. All right, so I have 8 numbers, 8 positions. All right, so great. So I know this is 4 and 5. That's why I put 4.5 and 4.5 there before. But the next rank up is 6, because remember, this was both 4 and 5. The next one's 6, so it's 6, 7, and 8. So the midpoint there for this is going to be 7, 7, and 7. So 6, 7, and 8, 7 is the middle number. So that's the reason I mentioned you should write the order numbers down first before moving on to fixing the ties, is so that you can actually see that these 2 numbers normally have the positions of 4 and 5. That's why they're getting 4.5. And you don't do this thing where you sort of collapse and think, okay, this next one is 5, 6, and 7, when really it's 6, 7, and 8, because 4 and 5 are both used here. So all we're going to do is sort of make sure that we take any tied values, because anything that scores a 6, well, anybody who scores a 6 should have the same percentile rank. Anybody who scores an 8 should have the same percentile rank. So we've got to make sure they have the same ranks in the data set. Here's another place where you might find some variation in terms of how things are addressed. So I've seen in places online where you might find that it says that for values, like when you have ties, to fix the ties by assigning the lowest value. So it'd be 4 and 4, and then 6, 6, 6. Or to apply the highest value, so it'd be 5, 5, 8, 8, 8. There's nothing wrong. There's no wrong way with which to sort of do this. This is just the most common way. Again, Excel, SPSS, those kind of places where you ask for a percentile rank, this is the process that they're going to use. They're going to assign the midpoints, and then they're going to subtract the 0.5 in the percentile rank equation. So here is an example. We have this data set here, 9, 5, 2, 3, 3, 4, 8, 9, this whole long data set. Okay. Before you do anything when it comes to either percentiles or percentile ranking, the first thing you have to do is put things in order, or else you're going to be lost. If you start trying to apply percentile ranks or define percentiles for values without putting things in order, you're not going to be able to find the right answer. So the first thing I did was, okay, so I got this data set. I put it in order. So this is the same data set: 1, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 7, 7, 7, 8, 8, 8, 8, 8, 9, 9. So I just put it in order so that we can see where the ties are, where the repeat values are. So then the next step I would do is just to order them. So this is 1, 2, third number, 4th, 5th, 6th, 7th, all the way down to the 21st value. I just ordered them from 1 to 21. So now I know my n. I know my n equals 21, and I have all the position numbers that I would need all the way through here. So the question over here says, what is the percentile rank of 3? All right, so the value 3 here is in this. This is the these are the numbers that I'm interested in terms of asking this question. How do I find the percentile rank for those numbers? So first I need to find the ranks. So the order numbers 3, 4, and 5, I'm going to assign the midpoint to those. So that's just 4, 4, and 4. So the value of 3 gets a rank of 4. There's 4 4s. I'm sorry, there's 3 4s, 4, 4, 4. They have position numbers 6, 7, and 8. I'm going to assign that midpoint there, so it ends up being 7, 7, 7. 3 5s, their positions are 9, 10, 11, so they get ranks of 10, 10, 10. There's only one 6. 6 is in the position, the 12th position, so its rank is 12. Down here I have 4 8s. Their positions are 16, 17, 18, and 19. So I'm going to assign 17.5 to all 4 of those. There are 2 9s in the 20 and 21st position. And I'm going to assign 20.5 to both of those. Okay, and then I can apply this equation here on the side, percentile rank equation, to any one of these ranks, and it'll give me my percentile rank. So let's see how that works. So the rank for 3, the percentile rank for the value of 3 in my data set equals its rank, which is, my head's in the way, 4 minus 0.5 divided by 21. So that makes this 3.5 over 21. 3.5 divided by 21 is 0.1666667. So I multiply that by 100. I get that the percentile rank for the number 3 equals 16.667%. Right? I didn't write the percentages, the percents here, but these are all the same thing. So we asked the percentages of scores that fall below the number 3 is roughly 16.667%. So the percentile rank tells you what percentage of scores fall below that value. So it's important to think it's below that value. That's the reason why it's a minus 0.5. Okay, so if I didn't subtract the 0.5, I would have used 4, which technically means I would have said I want to take the middle part of this 3 of the 3s, right? And I want to find out, because we assign 4 to all 3 of them as their rank. There's 3 4s. It's going to include a part of the 3s in the equation. By subtracting out the 0.5, I'm actually moving it to a point that is below those numbers and doesn't include any of these in there because they're all rank 4. So by subtracting 0.5 here, I'm essentially moving the apparent limits on that particular rank to its real limit, so that the limit that's below the actual value, so that I can ask the question or answer the question, what percentage of scores fall below that rank? If I instead had used, or here's a different color, if I instead had used plus here, it'd be asking a different question. The question with the plus is, what percentage of scores fall at that number and below? So do you want to include the number in the percentage, or do you want to know the percentage of scores below it without including that number in the percentage? The subtraction removes the number and calculates the percentage for numbers below that number. The plus 0.5 moves it above that number so the number gets included in the percentage. So do you want below or at and below, which are the two different approaches typically to looking at percentile ranks? The most common is the below one. So when you get back your percentile rank on the SATs or the GREs or LSATs, MCATs, all those different kinds of tests, and tells you that your percentile rank was 92, well, that tells you that 92% of other respondents did worse than you did. Or another way of saying it is you did better than 92% of other respondents. It doesn't include 92 in that percentage, or it doesn't include your score. It includes everyone who scored below your score. So that's why we subtract the 0.5 to move it below the number we're interested in, so it does not get included in the percentage. So percentile ranks are specifically asking what's the percentage of scores below that number. It doesn't include that number in the percentage. All right, that's percentile rank. That's when you have a particular score, like 3, in your data set, and you want to know, all right, well, what's the percentile, what's the number of scores below this number? You use the percentile rank. What if instead I have a particular percentage in mind? So if I'm going down here, notice that like 50%, exactly 50% isn't here. Exactly 75% isn't here. Neither is 25%. Right? There's nothing that falls at these nice, neat categories. I mean, even this is 80.952%, not exactly 80% or not exactly 90%. So if there's particular specific percentages I'm interested in, then we need to approach this a different way. I can't take the percentile rank equation because that just tells me the rank of scores that I have. I need to switch over to looking for percentiles, not percentile ranks, but percentiles, where that will tell me what number, even if that number doesn't exist in my data, will fall at a particular percentage. So let's switch over to talking about that. And that becomes a little bit more complicated. There's more steps to that, and there's a fun process called interpolation that gets involved when it comes to percentiles, because we start talking about numbers that we don't even have in our data set. We're making up stuff. We're making up values that if we had this value in our data set, we would be at this specific percentage that we're interested in. All right, so we got to figure out what those numbers would be. And that takes sometimes a little bit of educated guessing. Not really educated guessing. It just takes a little bit of thinking about the pattern of points along a line and figuring where it might be, and so that's what interpolation is. So if I want to find the percentile, this is the down here at the bottom, the use. I have a specific percentage in mind, like 75% or 80%, something exact. Like on the test, if you know you have to have an 80% or better to get a B. So this is sort of figuring out, okay, well, what score do I need to have on the test to be better than 80% of students? Okay, so it's asking the reverse question. I have a specific percentage in mind. I want to know what the score is. Or the last thing we're doing, the percentile ranks, I had a specific score in mind, and I want to know what percentage corresponded. This is the reverse. Okay. So how do we find a percentile? We're going to use this equation, but this equation doesn't give you the answer. Okay, what you get from this equation is not the answer to the question, like what's the number, what score do I need? It just tells you, this tells you where to find it. Right, so it's not going to give you the score exactly. It's just going to tell you where to find the score in your data set. So the XP, this first part of the equation, is the position of the score at the desired percentile. So if I want to find what X is at the 75th percentile, this would be X75. And then the P is going to be the proportion that corresponds to that number. So this is 75%. I want this to be 0.75. This is the percentage we're interested in. This is the proportion that corresponds to it. So 0.75, okay? N is the number of scores. And then you got 1. This plus 1 is always plus 1. Okay, so it's N plus 1. It's always that way in this particular thing. We're not going to subtract. We're not going to do anything. We're just going to add 1. All right? So the N is the number of scores. And it should be if the value you get here, when you plug this in, is an integer, like a whole number, then all you got to do is go to the number in that position. All right, the fifth, this ends up being, let's say you plug this in, you get 5 as your answer. Then you go to the number in the 5th position, look at the number in the 5th position, that's your answer. Okay, so this tells you where to find that score. Again, if it's a whole number, then just go and find the number that's in that position in your data set. That's it. That's your answer. However, if it's not an integer, like it's got decimal sort of proportion attached to it, right? The percentile is not a value that's in your data set, and you need to use interpolation to find it. Interpolation is defined over here. The insertion of an intermediate value or term into a series by estimating or calculating it from surrounding known values. That sounds, you know, super fun, but it's actually not that hard. It's basically the idea of if I have a series of points like this in a pattern, but for some reason I don't have points that fall between these points, I wasn't able to collect data then or something like that. What interpolation says, all right, if these points are sort of already going in this general sort of pattern, I can probably interpolate these points here. I can guess based on the patterns of other points, based on the rest of the information I have. I can actually interpolate these values from other information. Okay, and you may have heard the term extrapolation. That's the same idea. So I have points going this way, and I can't collect data anymore after this. Right? So this is my last data point going here. And someone asks, well, where do I expect, you know, if you were to make an observation out here, where would you expect the data to be? Well, I don't have this number, but I can take this value and expand it out to points in which I have not collected beyond where I've collected. And I can extrapolate this pattern out to a new data point way out there. So that's extrapolating, going beyond the data that I have. Interpolation is taking the data that I have and guessing values that are in between values that I do have and I did collect. Okay, so with that being said, the way we're going to do with percentiles, we're going to find a position, if it has a decimal place to it, a proportion attached to it, we're going to use that proportion and the pattern, the numbers that we do have in our data set, to then figure out where that data point might exist, if it did exist. We're going to interpolate. We're going to find a point that matches our criteria, our percentage. It may not be one that's actually in our data set, but that's okay. We're going to say if it did exist in our data set, this is what we expect it to look like. All right, so that's finding the percentiles. I have a specific number in mind, and now I'm going to go and find that specific number. All right, so let's take this over here. Let's talk about how that works, because this is probably one of the places where I think students traditionally in the class actually have some difficulty with it, trying to understand how to find scores and how to interpolate. How to do all that stuff. So let's do some examples. All right, let's say I have, so first I'll give you an example and sort of we'll walk through it and then we'll do a couple more. So let's say I'm given some data set and it has these are the numbers, and I've already went through the process of putting them in order, right? So I want them to be from smallest to largest. So I did that. 1, 4, 9, 16, all the way through. Okay. So let's say I want to find the 75th percentile. All right, or let's say whatever it is I want to find, I end up with a number that is 7.5. I want you to think of those two pieces of information as I want you to think of them as two different pieces of information. So one, this 7 tells you where to start. Where do I start looking? Right, it's going to orient you to the place where you need to go to find your new score. So I'm going to go over here to the number in the 7th position. Right? So this is where I'm going to start looking. All right. Now, the second part of what you get from the XP equation is this 0.5. That number tells you, it sort of hones you in a little bit further. It tells you exactly where to look. So 7's where you start. The 0.5 tells you that it's the number you want, the number you're looking for is halfway between the number that you're starting with, 7, and the next number. All right, so I'm getting 7.5, so it's halfway between the 7th and 8th numbers. All right, so I know that the 8th number is here. I got to figure out, all right, well, I need a number that's halfway between the 7th and the numbers in the 7th and 8th positions. Those two numbers are 49 and 64. So I need to figure out, well, how do I get halfway between 49 and 64? All right, well, let's start with 49. And I start counting. 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64. And I figure out how many steps there are in between those 2 points. Okay, so I can do it like this as a graph, but I can also figure out, all right, 64 minus 49 is 15 points. So it tells me that there are 15 steps between 49 and 64. All right, well, I don't want to go all 15 steps, right? It's telling me up here that I only need to go halfway in between. I need to go halfway the distance between the number in the 7th position and the number in the 8th position. So 15 steps, so all I need to do is take that 0.5 and say I'm going to take my 15 steps and I'm going to take that times 0.5, because that 0.5 came directly from here. So 15 steps between the two of them times 0.5, so it's half of that. 15 times 0.5 gives me 7.5. So this equals 7.5. Okay, so that means the number that I want is 7.5 steps beyond my 49. Right, so this is where I'm starting from. If I take 49 and I do 7.5 steps, 49. So that's 1, it's 50, 2, 51, 3, 52, 4, 53, 5, 54, 6, 55, 7 is 56 and a half. I get right to this 56 and a half point. So this 56 and a half is the number that is in the 75th percentile, or whatever. It's the number that I found, whatever I was looking for, it's the number that I found based on this XP equation. This is actually the percentile that I'm interested in. Right, so this is the actual answer. 56.5 is my answer. It is the number that is halfway between the values in the 7th and 8th positions based on this XP equation. That's what this is telling me. I want a number that's halfway between 7 and 8. So the numbers in 7 and 8 were 49 and 64. So I figured out there was 15 steps in between them. I found halfway between that was 7.5. So 49 plus 7.5 is 56.5, and that's my answer. All right, so that can be a little bit overwhelming. There's a lot of steps in there, a lot of things. So I try to break it down into steps that you can follow that will lead you to the correct answer sort of each time. And then the more you do it, the more comfortable you'll get, and you'll be able to sort of see it coming long before you go through all those steps. It starts becoming a little more natural. So in the beginning, when it's not so natural, let's follow some very hopefully easy to follow steps to sort of get to our answer. All right, so let's talk about that. So that was a sort of quick way of thinking about it. So let's talk about what those steps might look like. Let's label the steps that we just went through so we can actually refer back and sort of do them over again. Make it more replicable. Okay? So here are the steps. First, apply the equation. Great. So whatever I'm looking for, if I want the 88th percentile, I'm going to put 88 there. This is 0.88. It's the number of scores I have plus 1. I'm going to plug numbers in. Where XP is going to come out to be in some format, where it's going to be number dot number, like 5.7 or whatever the numbers are. we can think of those two as two different pieces. The first number is place 1 or position 1, where the part after the decimal is the proportion. So I'm going to break the answer into looking for place 1 and proportion and the proportion values so separately. Again, place 1 tells me where to start. The proportion tells me, well, how much above place 1 am I looking for the number? Or how far between place 1 and 2 am I looking for the number? Like in our last case, it was 0.5, so I know I wanted to go halfway between place 1 and place 2. But it won't always be half. That's the issue. Okay? Find values in place 1 and place 2, because place 2 is just the next adjacent number, right? The next highest value in your data set. I'm going to find those two numbers, not the places, but the numbers in those places, the actual data that are in those two places, and I'm going to subtract them. And by subtracting them, I'm going to create the total distance, the distance between the numbers in the two positions. I'm going to call that distance 1. But I don't want the full distance. I want the proportional distance. I want the distance that is indicated by the proportion that I want. I want half the distance, or 0.8 the distance, or 0.2. I want some proportional part of that. So to find that, I'm going to take that distance 1, the distance I just found here, take my proportion and multiply it by that distance. And this gives me my distance 2, or you can call that your proportional distance. And I want to add distance 2 to the value in place 1, and that's the interpolated value. Okay, so find the two places, the numbers in the two places, subtract them, take that, multiply that by the proportion you found up here, add that number to the number in the first position that you found by this number here as well. And when you add those together, that number is your interpolated percentile. It may sound complicated, like way too many steps. You do it a couple times, you're like, oh, this is easy. But you got to practice. You got to sort of dive in and do it and make mistakes and figure out what's going on. And once you do that a couple times, you can sort of jump right to the end of it without doing all those steps. These steps are just there to get you to practice and sort of follow all the steps along. So let's go through it, and we'll do it, sort of this sort of slow way and figure this out. So here are the same, I think they're the same numbers that we had a second ago. They're exactly the same numbers. Yeah, same numbers, nothing different. But now I want to find a number that's at the 66th percentile. Okay, 66th. Doesn't sound too hard. And maybe I can go down here. I'll take a knee here, and I can go through this. Let's go through this a little bit at a time. So what was step 1? Let's go back a second. Step 1 was apply the equation. Okay, do that. So the equation is, I might just kick something back here. Hold on a second. Okay, so the equation is, I want my x for 66. That. And I'm going to apply that here. I'm going to take my p, 0.66, and it's just the same number as a proportion. And I multiply that by n. So again, I have 9 numbers. So 9 plus 1 is 10. So that means the number that I want is the number in the 6.6 position. So I'm going to start with the number in the 6th position. And the number I'm looking for is 60% of the way between the 6th and 7th numbers. Okay. So this tells me this is place 1. Right? Place 1. So I'm going to go here. Now let's mark that off. This is my place 1. Place 1. Awesome. Found that. First part's easy. That means that place 2 is simply just the next place. Cool. So I got my place 2 as well. So the steps say, all right, find the values that are in those two positions, all right, which are 36 and 49, and we need to find the total distance between them. Okay, so distance 1, I'm simply going to subtract the numbers in the two positions. Place 2 minus place 1. So that's 49 is the number in my second place, my place 2, minus 36 equals 49 minus 36 equals 13. So my distance 1 is 13. But that 13 is the entire distance. It's the whole distance in between. So that means that if I go from 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. Okay, that's the distance, the whole distance in between those two numbers. I don't want that though. I only want 60% of that distance. That's the number I'm looking for. How do I know it's 60%? Because this told me. I want a number that is 60% the distance between 36 and 49. So I don't know what that is, but we can figure it out. If the total distance is 13, distance 2 then equals, distance 2 equals 13, which is my full distance 1, times the proportion that I'm interested in up here, 0.6. So I take my 13 times 0.6, and I get 7.8. So 7.8 is my distance 2, so my proportional distance between the numbers in the 6th and 7th positions. Now this tells me, this is how many units is 60% the distance. But to figure out what that actually looks like, my actual percentile, I'm going to take the number in the smaller position, 36, and I'm going to add in the proportional distance. 36 plus 7.8 equals 6 plus 7 will be 13. Right, so that's 43. Yeah, 43.8. And then 43.8 is the answer. This is the interpolated value. It's not a value that exists in our data set. It's just saying that if this number existed in our data set, 66% of the scores will fall below it. Let's try a different one. So let's go to the other side. This is the 33rd percentile. All right, so it's going to be similar idea. 33rd. So x33 equals 0.33 times 9 plus 1. Okay, so that means this is going to be 3.3. So I want a number that is 30% of the distance between the numbers in the 3rd and 4th positions. Okay. All right. So the number in the 3rd position is the number 9. All right. So here's place 1. The number in the next position higher is that one. So this is place 2. So what we need to do is sort of plug some of that stuff in. So let's find my distance 1 is the full distance in between the numbers in the 4th and 3rd positions, or 3rd and 4th positions. So I'm going to take the number in place 2, 16. Now subtract from that the 9 in the first place, in place number 1. 16 minus 9 is 7. But I don't want, again, so let's go back to thinking about this visually. I got 9. I gotta go 1, 2, 3, 5, 6, so 16. So that's 9, 10, 11, 12, 13, 14, 15, 16. So the distance between 9 and 16 is 7 steps. There's 7 steps to go from 9 to 16. But I don't want all 7 steps. I want just 30% of them, 0.3 of those steps. So to find distance 2, like that, I'm going to take my distance 1, multiply that by my proportion that I found up here. So 7 times 0.3. Is 2.1. So that means the point I'm looking for is 1, 2, I don't know, somewhere in between here, right? It's like not quite 2. It's I mean, it's a little more than 2. It's not quite 3. So somewhere in here is the number I'm looking for that is 2.1 units above the number in place 1. So I can just do that. I can say my percentile equals 9 plus this distance, 2.1. Right, which means it's 11.1 is my answer. Okay? And this is the percentile. So the number I've been looking for this whole time is 11.1. That is 0.3 the distance between 9 and 16. Again, it's not a number that we have in our data set, which is why we had to interpolate. It's basically saying if this were a real number that we had in our data set, 33% of scores would fall below that number. All right? That's how percentiles work with interpolation. All right. There's some more. I think there's a link online to some additional sort of video links, and there's another one that does more of this stuff, some more examples, and it might be sort of useful if you're still not quite getting it. But there's no way really to get this unless you sort of jump in and do it. So jump in and try to figure out what these are. What would distance 1 be? What would distance 2? Should have a C. What would distance 2 look like? This is the sort of proportional distance. You know, what numbers are in place 1 and place 2? Like, just go through and start figuring that stuff out. And the more you do it, the more practice you do with it, the better, the more it'll make sense to start to click in a little bit. All right, so what's the point? Actually, let me see if I have another example. I don't think so. I think it goes next to talking about, well, what does this mean? We're talking about all this stuff. What does this have anything to do with variability, which is the very topic we're in? Well, because we started talking about interquartile ranges, which is a kind of measure of variability. And you can't really talk about what a quartile is without really understanding what percentiles are. So what you see here, let's talk about, okay, before we get to that, I do have one. This one should be really easy. Whenever it says the 50th percentile, and you start to think to yourself, oh wait, all right, here's XP, X50 equals 0.5 times 9 plus 1. You start doing all this work, and you say 0.5 times 10, well, that's just 5, right? Okay, well, cool. 5. 1, 2, 3, 4, 5. Sweet. That's a lot less work. I don't have to do them a whole lot. Here is my number. So the percentile here equals 25, based on our XP equation. But you sort of already knew that, because if I have an odd number of 9 scores, the number at the 50th percentile, we also call this the median, right? And you already know that the median, if they have an odd number, is just the middle number. There it is. So if you see something like this, the 50th percentile, instead of going through all this work, to apply the equation, that kind of stuff, just think, wait, 50th percentile, That's the same thing as the median. I just need to find the number or numbers that are in the middle and figure it out. I don't need to do this equation. But I wanted to show this because this equation does sort of verify. You do get this. You get the same number, right? You get the same value doing it this way. It's the number in the fifth position. Okay, if you go there, cool. Well, yeah, that's because it's the number right in the middle. It actually works that way as well. Okay. 50th percentile, median. Tie those two, ideas in your brain together. It can save you a lot of time on a test instead of sort of going through all the steps to find all that stuff. You can just find the middle value and know that that's the 50th percentile because it's the same as the median. Okay. Let's go on. Apparently I put this in I could have put this in a stranger place. It's like right directly across my face. I may have to move that up or down or something. I don't know, it's a weird place for it. Okay. Quartiles. So the whole detour, the whole thing we're talking about was to get us to the point where understanding what a percentile is so that we can talk about what is a quartile. To calculate quartiles, you simply find the scores at the 25th, 50th, which is just the median, and 75th percentiles. And once you have those, you simply subtract the numbers in the 25th and 75th, and that's your interquartile range, which is how this fits into the variability discussion or chapter. So let's go back to variability. All right, so that's the end of the detour. So we detoured into talking about what the hell a percentile is and how it gets calculated, just to come back and say, okay, now that we have this idea of what percentile is, let's actually apply it. So we can then find P75, which is the same thing as Q3. We can find P25, which is the same thing as Q1, and then we can subtract them. If we subtract Q1 from Q3, we get the interquartile range, which is the spread across the middle 50% of our data. So it's cutting off the highest 25% and the lowest 25%, looking at what's the range for the values in between. This helps a lot to get rid of data that have outliers or their skewness. It can sort of help to normalize the data somewhat so you're not looking at or being influenced by super extreme scores. If you find the score that is at the 75th percentile, let's go back and look at our data real fast. Let's go back. So forget about the 50th. Let's look at the 25th. Let's do the 25th, and so let's look at P25 equals 0.25 times 9 plus 1 equals 2.5. And then P75 equals 0.75 times 9 plus 1 equals 7.5. So 7.5 we already did, but let's just do it again, just for the sake of argument. I'm going to do this quick form this time and not go through all the steps. Let's just do it sort of fast. So 0.25 means 2.5. It means I am going to start here and here, and I want a number that's sort of 0.5 in between them. The numbers are 4 and 9, so I get 9 minus 4 equals 5. 5 times 0.5 equals 2.5. I add 2.5 back to the number that's in the second position, and it tells me that the percentile here, I should say P25 equals 6.5. Okay, 6.5. Same thing, we did it for, 0.75 already, but let's just do it real quick. So again, 0.75, 7.5, I want the numbers that are here and here instead. And again, I want the number that's halfway in between. So I can take 64 minus 49 to get my distance. And I already forgot what that was. That's what's the 59 is 10. So it's 15. So there's 15 units there. Multiply that by 0.5. Ends up being 7.5. So P75 equals the number here, 49, plus 7.5, which gives me 56.5. Okay, so just really quick, the range, regular old range here equals the maximum, 81, minus the minimum, which is 1. So my range is 80. Super simple to compute. Okay. Now, interquartile range, my IQR equals my 56.5, that's my Q3, minus my 6.5, that's my Q1, and I get that this is 50. So my range is 80, but my interquartile range is 50. And this is the range of the entire data. This is the range of the middle 50% of the data. So it's the middle part. It's removing the extreme scores like 81 and stuff out of the picture so that you're getting a more stable estimate of how far scores are spreading apart. Okay, so that's how we can apply the P25, which is Q1, and P75, which is Q3, find the values and subtract them to get the interquartile range. All right, that's good. These also come up in a place you may or may not have realized before. You may have been looking at or seeing things that are in the interquartile range or using quartiles without knowing that they were there. If you've ever looked at or tried to interpret a box plot, or a box and whisker plot they're often called, then you've actually been looking at values that correspond to quartiles. So let's look at what I mean by that. So if I go forward a little bit here. So when looking at looking at a box plot, whenever you see these box plots, box and whisker plots, you may have seen them this way, sort of sideways, but you may have also seen them. I lost my other marker. You may have seen them going this way instead. There's a range of values or something from like 100, and I don't know, up here to 0, and then there's the box here, the thing there, and then the whisker there, whisker there. So you may have seen them going this way. These are sort of what they call box plots or box and whisker plots. What these values correspond to, if you're actually looking here, typically, this is technically without outliers. So with no outliers, it's a fairly easy interpretation. This is the minimum number. This is the maximum number. Okay. So if we were doing this for our own, I could say this one is like 81, right? And then our minimum number was 1, right? So it's a 0. There's 1. That was our minimum. And then it was 6.5 or something, right? 6.5 was our lower, was our Q1, and 56.5 was our Q3, and the median ended up being 25, if I remember correctly. Go back a second. Yeah, 25. So somewhere in here is at 25. Because what a box and whisker plot does is, again, it indicates the minimum and the maximum based on these whiskers. The box is actually made up of this is Q1, this is Q2, also known as the median, and then this is Q3 up here. So the box tells you how many, what the interquartile range is, and the whiskers tell you the range. Where the Q2 is, if it's right in the center, it tells you it's sort of more symmetric. If it's sort of to one side or the other, it can tell you a little bit about the skewness of the distribution. They oftentimes call this part, right, they call this thing the box length. Box length. Oops, box length. Well, the box length is just, it's another term for interquartile range, right? How the width of this box going this way tells you what the interquartile range is. Right? If you look at the number that corresponds to these 2 points, if you were to subtract them, you would get the interquartile range. But in terms of a box and whisker plot, they call it the box length. Sometimes you'll see, this is, again, if there are outliers, okay, sometimes, I'm not going to go too much into this because it can get complicated, but if you try to do a box and whisker plot through something like SPSS or some other program like that, they will include outliers by, they'll put little things up here like this. They'll have a little, a little asterisk that indicates that while most of the values fall between these things, there's an outlier. The way they figure that out, it has to do with the box length. They take the box length, and it's 1.5 times the box length. So you look at take the Q3, you look at 1.5 times that box length, here, and anything above that then becomes an outlier. Same thing down here, anything below 1.5 times the box length becomes an outlier. Some programs will even go as far as in having another stage of outliers where it's 3 times the box length is then an extreme outlier. But so if you ever see these little stars written out, I think you might actually see that in your lab. Those stars are being put there because they're figuring out what the interquartile range is, putting that then 1.5 times that above there to see if any values fall above that. If they do, then they're outliers. Okay, but that's not something that, if you're asked to make a box plot or something as part of your exam, you don't need to worry about outliers. Just give me the minimum, the maximum, Q1, Q2, Q3, make the box, make it nice and pretty. That's it. You don't have to worry about asterisks and outliers and all other stuff. What time is it right now? Okay, we're going to wrap this up pretty quick. We started a little late, so I'm going to go just a little bit further, try and wrap this up so we can be done and have all this finished. So we talked about the interquartile range, and those are all have to do with the sort of range, how far things are spreading. So let's talk about the variance. So the variance is the average square distance, aka deviation, of each score from the mean, also known as the mean square. The variance of a sample is usually written as S squared. The variance of the population is usually sigma squared. And here we have, you saying what? Because reading this, it's not the easiest thing to understand just as a definition. Just why I need to go in to look at the equation of it. So when calculated for a sample, okay, we're going to take, this is a variance. We're going to take each score minus the mean for the scores. For each one of those, we're going to square it. And then we're going to add in the next one. So we're going to do that for every single person. Take their score, subtract the mean, square it. Do that for person 1 through n, right? And then we're going to take n minus 1, degrees of freedom, divide that up, and we're going to get a sample variance, this S squared, sample version. When you calculate this for the entire population, meaning that you don't have to worry about, it's not a sample, it's everyone you're trying to estimate for, you can simply calculate for the entire population by doing the same process but dividing by n. Now, to be technically accurate, this is a little bit goofy, and I think I remembered this from the last time I used this slide. This is weird. It should really be, if you actually have the population, it really becomes sum of all of the values, x's, minus the population mean that you already have, squared, over n. Okay, so it's not necessarily mx, because mx is the sample mean. It really should be the population. So this is a little bit misleading. We're going to use the population mean, therefore we can use the entire n, because the population mean is known. Therefore, we can use n. All right. There's a lot of confusion about, well, I don't understand which of these am I supposed to use? There's this population version, there's the sample version, there's a version with n minus 1, one with n. People get really confused, and people that write the books for stats don't make it any better either, because I've seen this one called the sample, I've seen this one called the population, I've seen this one called the sample, this one called the population, and it really has to do with your perspective on things. And without getting into a whole lot of issues or a whole lot of discussion about how it should be and what my opinion is, it doesn't matter. Here's an easy way to remember. Okay, this is the one that you're going to use. This is the one that you don't use. Use this one, don't use this one. Now, if you're working on a problem and it says something like calculate the variance for this population, it specifically says that's a population, then yes, you can use this. It doesn't mean don't use it in terms of never use it. What I mean is, this is the one you're going to use like 99% of the time, and under rare special occasions you're going to use this one. And why? Because this one corrects itself for the fact that it's a sample when trying to estimate the population. We almost always, again 99% of the time, are dealing with samples. We're taking samples from the population, we want to do stuff to them, we want to infer meaning back to the population. So since we're dealing with samples all the time, this is the variance we're going to be estimating all the time, because we want to use this to try to estimate this in the population. Now, unless we have an entire population, we don't care about inference, we're going to be using this one, not that one. So this is one of those cases where you can assume, and I know what they say about assuming, don't assume because you're making an ass out of you and me, but you can assume under this case that if I say here's some numbers, what's the variance, I mean this one. The only time that there'll be again a special occasion for that is if it says something, here's some numbers, assume that this is a population, then you're supposed to use this one. But if it doesn't say anything, assume this one's the one that's required. Okay, so let's talk about how that works. So remember before we had found out 2, 4, 6, and 8. First we got to find the mean. 2, 4, 6, 8. I think we already did that, but let's do it one more time. 2 plus 4 plus 6 plus 8 equals 20 divided by 4 equals 5. Okay, so the mean is 2 plus 4 plus 6 plus 8. Alright, so that's 10, so this equals 20. And there are only 4 numbers, so 20 divided by 4. This means I have a mean of 5. Okay, so our mean for x is 5. Great. So now I need to find deviations for each one. That means I'm going to take 8 minus 5, that's a deviation, 6 minus 5, 4 minus 5, and 2 minus 5. These 4 numbers, I get 8 minus 5 is 3, 6 minus 5 is 1, 4 minus 5 is -1, 2 minus 5 is -3. So this is one of the interesting things about this. So these are just the deviations. How far is each score away from the mean? If I look at just the deviations and I try to sum them, the sum of this is 0. I have to sum the deviations. 3 plus 1 is 4, plus -1 is 3, plus -3 is 0. So this is sort of a fascinating aspect of the mean, is that if you actually calculate the mean, subtract it from all the scores, you're going to get the sum of the deviations is going to be 0, which is why we tend not to sum the deviations. We tend to square and sum them. We tend to want to sum this, to do the sum of square deviations, not just the deviations themselves, because it doesn't get us very far if we sum the deviations. We're going to get 0, or a number very, very close to 0 each time we do that. So instead of just summing them, I'm going to square them first. So let's square them first. So we said this was 8 minus 5 this was 3, 6 minus 5 is 1, 4 minus 5 is -1, 2 minus 5 is negative 3. Oops, I do that a little too low. Negative 3. Okay. Negative 3. So if I square it, that means this is 9. This is still 1, that's still 1, that's still 9. So that's 10 plus 10. I have the sum of all this stuff equals 20. Okay, this is the sum of square deviations. This is the sum of each score minus the mean. All right, inside these parentheses is this. All right, so the deviation is inside the parentheses. All right, so 8 minus 5, 6 minus 5, 4 minus 5, 2 minus 5. But I'm not doing that. I'm actually squaring it. So I need to square each one of them. So I'm going to take 8 minus 5 is 3. 3 squared is 9. 6 minus 5 is 1. 1 squared, still 1. 4 minus 5 is negative 1. Negative 1 squared is 1. And then 2 minus 5 is negative 3. Negative 3 squared is 9. And then I did it for everybody. Now I'm going to sum it. So I summed all those. 9 plus 1 is 10. 1 plus 9 is also 10. So 10 plus 10 is 20. So this whole top part here for this particular problem equals 20. The sum of xi minus mx squared, the sum of the square deviations for these 4 numbers in this data set is 20. All right, great, awesome. What do we do with that? Why do we care? Once we have the sum of square deviations, I want to get something like an average. I want to know sort of on average how much do people deviate from the mean. So I could just divide by n to get an average. That's how we typically get averages. So I can do that. But so we figured out this was what, 9 plus 1 plus 1 plus 9. Those are deviations. And then down here we have it's 4 minus 1 is 3. So that ends up being 20 over 20. I figured out this is 20, and then it's 3 on the bottom. So 20 divided by 3. Not so easy. That is a 20 divided by 4 we did a second ago. 20 divided by 3 equals 6.667. So this is 6.667 is my variance. Okay, so that means that scores in this data set, this 8642, scores in that data set deviate from the mean 6.667 squared units on average. All right, so 6.667 squared units on average is how much people deviated from the mean. And you can sort of see it's that unit squared thing that makes it sort of difficult. So, you know, we don't want to often deal with that. So once we find the variance, typically the next step is to let's convert the variance over to a standard deviation. Variance is in squared units, which we don't really want. So we want to go to regular units that we were measuring in the first place. So why don't we just do that? So we take the standard deviation is just taking the variance and taking the square root of it. So since our variance was 6.667, we can take that number, 6.667, and we can take the square root. So 6.667 square rooted is 2.582. So this equals 2.582. So 2.582, that makes a lot more sense, where we go, okay, the average is 5, and the units deviate from 5 about 2.582 units on average. So you could sort of say that this data set is, all right, well, and it has an average of 5, sort of plus or minus 2.582, sort of what the meaning of the standard deviation is. All right, so plus or minus 2.582 around that mean gives you an average amount that the scores deviate around the average. Okay, Next slide. Go back a second. Just as an aside, just to make this sort of complete, that really sort of is the complete lecture topic-wise. But I do want to talk about one thing really quick that comes up quite a lot because of different ways in which people teach this stuff. So I'm giving you this equation here that is the sum of each score minus the mean squared. This, I usually refer to this sort of as I think of this as the deviation form of the equation, right? So it's the equation in terms of deviations from the mean. What's the square deviation from the mean? In other places, you'll see the same equation, the equation for the variance for standard deviation written this way. And whatever reason, just to sort of separate out, I usually think of this as the sort of computational form. You know, they're both computations, but so oftentimes we refer to this as the sort of computational form. What this does is it takes the idea of squaring and subtracting things, and it just sort of mathematically, algebraically rearranges them. So I'm taking scores and I'm squaring them. I'm taking the averages and squaring all this other stuff. What this is doing, because since the average is simply just the sum of all the scores divided by n, it's really taking the sum of all the scores, right, divided by n. But because it's in this parentheses, I have to square it. And I can then take the sum of all the squares here. So it really is just separating this equation out into component parts. The reason why people like it is because it oftentimes can be quicker, easier to compute if you're doing it by hand, especially if these values are given to you, like the sum of x squared or the sum of x. Sometimes this can be referred to as like the total, right? So if someone gives you a total of all the numbers, well, I already have the sum of x. I can just square it, and I can save myself a lot of time instead of going through and sort of subtracting out the mean and doing that over and over again. Now, you may be thinking, well, this is just 4 numbers. Whoop-de-doo. Yeah, imagine it's 400 numbers, or at least 30 even numbers. You have to subtract the mean multiple times. If somebody's already provided you the sum of all the squared values and the total, you can plug it into here, get an answer for variance very fast instead of having to go through and subtract the mean from all the scores. So if you look, this is, we already summed up the scores and found out the sum was 20. I squared every one of them, so 8 squared is 64, 6 squared is 36, 4 squared is 16, 2 squared is 4. Added up all the squared values and I got 120. So that means that the sum of x squared, let's go back over here, the sum of x squared, that's in this first part, right, equals that 120, and the sum of x equals 20. So I have those components. Do I actually do it here? No. So I actually have the components I need to figure this out, right? So I can compute a variance for this pretty quickly by saying, all right, the variance equals 120 minus 20 squared over n divided by n minus 1. All right. So 120. 20 squares 400 divided by 4 equals 100. So it ends up being 120 minus 100 over, and then it ends up being 3 in the bottom. Which is the same 6.667 we found before. And all we really needed was those two numbers. If you have to find the numbers yourself, like the sum x and to square all the x's and sum them, it's probably not going to take it's not going to be a whole lot faster to find this. It may be a little faster to just go through and square things and subtract them and square them, but not by much. It's only if these things are given to you that it becomes really quick and easy to plug them in and get the same answer without doing all the deviations and squaring. I would really focus on this form to understand what a variance is and what it does. But if you can, you want to be able to do it quicker and learn how, if there's a sort of quicker method to get the problems answered, like on an exam, then knowing this one is actually not a bad idea. But I would definitely focus on this one first, this one definitely second. Okay. Why do we like the standard deviation so much? Well, a big part of it is it relates very well to the mean. Okay, so it uses a measure of central tendency, specifically the mean, right? The mean is built into the problem. It actually is in the standard deviation. It's in the measure of variance. It also uses all the data points. Unlike the range or interquartile range that only use 2 numbers, standard deviation uses all of them. A bigger reason is it's connected directly to the normal distribution, to a normal curve. Okay, so we'll see this soon. We're going to talk about the normal distribution and how it works. We're going to see the standard deviation and the mean actually play a huge part. They're very connected. It's super useful. It's in lots of stuff, like the standard deviation of a sample is S, standard deviation of a population is sigma. We're going to use the standard deviation for things like t-tests and other equations like that. So it's very helpful, very useful to compute it relative to the range or other things that may tell you about how far scores are spreading, but they're not really used much for anything else. Then there's always this question of why the n-1. And this is a question that comes up a lot from students. Why do we divide by n-1 and not n? What's the big difference? So one way to think about this is populations are big, right? They're huge, they're infinite, they're these massive things, and yet samples are very small. So if I'm trying to estimate something large, huge population, right? Here's my population up here. And I'm taking a tiny sample out of there. Little guy, little sample. And I'm trying to infer meaning from this back to the population. I'm not going to get the same kind of spread in my sample as exists in the population. It's just not going to be possible. So I got to be able to adjust some. So as I take these samples out of the population, I'm going to adjust the standard deviation or the variance in here to make it more like the population by dividing it by a smaller number. So I'm taking the sum of square deviations, I'm going to divide it by a number that's slightly smaller than I expect to give a little extra boost, to actually overestimate this a little bit to be closer to this. And they've shown that in long run statistics, meaning if I do this over and over again, take a sample from the population, estimate the variance, put it back, and do this over and over again, if I use n-1, it's a lot more accurate. That this tends to be a lot closer to the population value, where n, if I use n instead, it's going to tend to be too small. It's going to be a much smaller estimate of the population if I use n. Okay? And also it's just this idea of degrees of freedom. So I know we call it degrees of freedom, but what does that actually mean? What does it mean for degrees to be free? It's a very strange concept. I remember I went through a lot of stats courses and they talked about degrees of freedom, and I'm like, yeah, degrees of freedom. And I didn't really understand what that meant. So what is meant by degrees of freedom? This is sort of the last thing I'll talk about or mention in here. So what do we mean by degrees of freedom? So whenever you want to do anything with data, you want to add up some numbers to equal a certain value. You want to take those numbers, add them up, and then divide by 4 to get a mean. You want to be able to find some specific, either have numbers add up to something or average out or whatever. So if I give you an example like this, where I'm like, look, I have 4 free spaces. Okay, so you can take any 4 numbers you want and plug them in here, but the only thing is that they have to add up to 4. What's that 4? They have to add up to 10. It's 4 numbers have to add up to 10. Okay. All right. So you're like, great. I'll just start putting the numbers in. All right, 2. Now I could have put negative numbers. I could have put huge numbers. I could have done whatever I wanted, but I started with 2. Okay. So 2. All right. I still have 3 spaces left to add up to 10. Great. So I added a number of 4, so that's 4 plus 2, I have 6 now. I still have 2 free spaces before I add up to 10. So I pick another number, 3. So 2 plus 4 is 6, plus 3 is 9. All of a sudden, this last space isn't free anymore. So what starts off seeming like, well, I can add up any 4 numbers I want to equal 10. If I have 4 free spaces like that, really only 3 of them are really free. Because as soon as you start to fill in 3 of those values, this space is now fixed. It has to be 1. It can't be anything anymore. It has to be 1 to make these other 3 spaces work, or the other 3 numbers work. This is the same thing as I'm adding up. If I'm adding up scores, the sum of xi divided by n equals some mean of x, right? So as I'm adding up a bunch of numbers, and they're going to average out to this mx. If I have 30, if my n is 30, well, I have a mean that's sort of a fixed number. Once I figure out what the mean is, it's a fixed value, which means that I lose 1 degree of freedom. 30 minus 1, because as soon as you start to add up all those numbers, divide by n to get a mean, one of those values is no longer free anymore. One of those values is no longer going to be able to be whatever it wants, because the mean is sort of being estimated. So as soon as I estimate something like the mean, I lose 1 degree of freedom. And it just so happens that our sum of xi minus mx squared, it uses the mean. So we're using something that we estimated already. So because we're using an estimate of the mean to figure out our variance, we lose 1 degree of freedom. Why? Because we estimated the mean. The mean is being estimated, which is why we're losing 1 degree of freedom, because somewhere in our data set, one of those numbers is not free to vary anymore because it's being fixed by the fact we have an average. That average makes at least 1 degree of freedom go away. So we lose 1 degree of freedom because we're using an estimate of the average that then forces at least one number to sort of fit in to make the average work. So that loss of degree of freedom sort of shows up down here, which is why this is oftentimes called the degree of freedom, or degrees of freedom. And up on top we have the sums of squares, the sum of square deviations. Sum of square deviations shortens to sum of squares over degrees of freedom.